Imagine for a moment that the universe we know, our planets, stars, and galaxies, are just one of countless others. What if our entire universe is merely a tiny bubble in an infinite ocean of other universes, each with its own laws of physics, different histories, and unimaginable wonders? This idea, as fantastical as it sounds, is at the heart of the multiverse hypothesis. It's a concept that challenges our very understanding of reality and stretches the limits of our imagination. From ancient philosophers to modern scientists, humanity has always been fascinated by the mysteries of the cosmos. Today, cutting-edge physics and cosmology are uncovering new evidence that suggests our universe might not be the only one. In this video, we're going to embark on a journey through time and space to explore the multiverse hypothesis. We'll dive into the scientific theories, meet the pioneering thinkers behind them, and uncover the profound implications of this mind-bending idea. Whether you're a science enthusiast or just curious about the universe, this journey will leave you with a deeper appreciation of the cosmos and perhaps even a few answers to the age-old question: are we truly alone in the universe? To truly appreciate the multiverse hypothesis, we need to travel back in time and see how the idea of multiple worlds has evolved through the ages. Our journey begins with the ancient Greek philosophers. As early as the 5th century BCE, thinkers like Anaximander and Democritus pondered the existence of other worlds. Democritus, known for his atomic theory, speculated that there were an infinite number of worlds, some like our own and others vastly different. These early ideas laid the groundwork, but it wasn't until the Renaissance that the concept began to take a more scientific form. In the 16th century, the Italian philosopher Giordano Bruno boldly proposed that the stars were distant suns, each with their own planets and possibly life. His ideas were revolutionary and controversial. Bruno's vision of an infinite universe filled with countless worlds was ahead of its time. Despite facing persecution, his ideas endured, inspiring future generations of thinkers. As science advanced, so did our understanding of the cosmos. In the 17th century, Isaac Newton's laws of motion and gravity provided a new framework for understanding the universe. Yet the idea of multiple worlds remained largely speculative. It wasn't until the 20th century that the concept of the multiverse gained a more solid footing, thanks to groundbreaking discoveries in physics. Albert Einstein's theory of relativity and the subsequent development of quantum mechanics opened new doors to understanding the nature of reality. Quantum mechanics, with its strange and counterintuitive principles, introduced the idea that particles can exist in multiple states simultaneously. This laid the foundation for the many-worlds interpretation proposed by physicist Hugh Everett in 1957. Everett's radical idea suggested that every quantum event spawns a new, branching universe, leading to a potentially infinite number of parallel realities. This was a pivotal moment in the history of the multiverse hypothesis. Today, the multiverse hypothesis is a vibrant field of study, explored by cosmologists, physicists, and philosophers alike. It challenges our understanding of the universe and invites us to consider the possibility that our reality is just one of many. Before we dive deeper into the scientific basis of the multiverse hypothesis, let's take a moment to thank our sponsor, Notion. Notion is the all-in-one workspace that helps you organize your thoughts, manage projects, and collaborate with your team. With customizable templates, powerful databases, and seamless integration, Notion adapts to your unique workflow, boosting productivity and keeping everything in one place. Ready to bring order to your chaos? Try Notion today with link at description. Now let's journey deeper into the science behind the multiverse hypothesis. Now that we have a historical context, let's dive into the scientific basis of the multiverse hypothesis. This is where theory meets observation, and the boundaries of our understanding are pushed to the limits. One of the key ideas supporting the multiverse hypothesis is cosmic inflation. This theory, proposed by Alan Guth in the early 1980s, suggests that the universe underwent an exponential expansion in the first fraction of a second after the Big Bang. During this inflationary period, tiny quantum fluctuations were stretched to cosmic scales, seeding the formation of galaxies. But here's where it gets really interesting. According to eternal inflation theory, this rapid expansion didn't stop everywhere at once. Some regions of space stopped inflating and formed bubble universes like our own, while inflation continued in other regions. This process could create an infinite number of bubble universes, each with its own distinct properties. Another fascinating approach comes from string theory. String theory attempts to reconcile quantum mechanics and general relativity by proposing that the fundamental constituents of reality are not point-like particles, but tiny, vibrating strings. These strings exist in a higher dimensional space, and the ways they vibrate determine the types of particles and forces we observe. In the framework of string theory, different regions of this higher dimensional space can lead to different physical laws. This leads to the concept of the landscape multiverse, where each region corresponds to a different set of physical laws and constants. Quantum mechanics also provides a tantalizing hint at the existence of multiple universes. The many worlds interpretation proposed by Hugh Everett suggests that every quantum event creates a branching of the universe. In this view, every possible outcome of every event exists in its own separate universe. These scientific theories, cosmic inflation, string theory, and quantum mechanics, provide a robust foundation for the multiverse hypothesis. They suggest that our universe could be just one of many, each with its own unique properties and laws of physics. Now that we've explored the scientific basis for the multiverse hypothesis, let's dive into the different types of multiverses that these theories suggest. Each type presents a unique vision of what a multiverse might look like. The first type of multiverse is the Level 1 multiverse. This concept is based on the idea that the universe is infinitely large and uniform. Beyond our observable universe, there could be other regions of space that are essentially the same as our own, but so far away that we can never reach or observe them. In a Level 1 multiverse, the laws of physics and constants are identical everywhere. The differences arise simply from the initial conditions and the random distribution of matter. So somewhere out there could be an exact copy of our Milky Way galaxy and maybe even another version of Earth. The Level 2 multiverse takes us further into the realm of cosmic inflation. According to this idea, different regions of space can stop inflating at different times, creating bubble universes. Each bubble universe can have its own distinct laws of physics and constants shaped by the particular way inflation ended in that region. In this scenario, our universe is just one bubble among an infinite sea of bubbles, each with unique characteristics. Some might have different particles, forces, or even dimensions, leading to vastly different kinds of worlds. The Level 2 multiverse is rooted in the many worlds interpretation of quantum mechanics. Every time a quantum event occurs, the universe splits into multiple branches, each representing a different possible outcome. In this view, there are countless parallel universes coexisting with our own, each resulting from different choices and events. Imagine every decision you've ever made creating a new branch of reality. In one universe, you might have chosen a different career, while in another, you might have taken a different path entirely. Finally, the Level 4 multiverse encompasses the broadest and most abstract idea, the ultimate ensemble. Proposed by Max Tegmark, this concept suggests that all mathematically possible universes exist. Each universe corresponds to a different set of mathematical structures and laws of physics, making this the most diverse and far-reaching form of the multiverse. In the Level 4 multiverse, the range of possibilities is truly infinite, encompassing every conceivable form of reality that can be described by mathematics. These 4 levels of multiverses, Level 1, Level 2, Level 3, and Level 4, offer a fascinating glimpse into the potential vastness and diversity of reality. Each type challenges our understanding of the universe in unique ways. To further understand the multiverse hypothesis, we need to explore the key theories and models that provide a foundation for these ideas. These theories not only deepen our understanding but also highlight the pioneering minds that have shaped this fascinating field. One of the most influential theories in this context is eternal inflation. Proposed by Alan Guth in the early 1980s, this theory suggests that the universe underwent a rapid, exponential expansion immediately after the Big Bang. During this inflationary period, different regions of space could have stopped inflating at different times, leading to the formation of multiple bubble universes. These bubble universes can have varying physical constants and properties, depending on the specific conditions in which inflation ended. This model supports the idea of a Level 2 multiverse, where each bubble represents a unique universe with its own distinct characteristics. Next, we delve into string theory, a groundbreaking framework that attempts to unify quantum mechanics and general relativity. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. These strings exist in higher dimensional spaces, and their vibrations determine the properties of particles and forces we observe. In string theory, the concept of the landscape multiverse emerges. This idea suggests that different regions of the higher dimensional space can result in different sets of physical laws. These regions form a vast landscape of possible universes, each with its own unique properties. Another critical model comes from quantum mechanics, the many worlds interpretation, proposed by Hugh Everett in 1957. According to this interpretation, every quantum event leads to a branching of the universe. Each branch represents a different possible outcome, leading to a multitude of parallel universes existing simultaneously. This model supports the idea of a Level 3 multiverse, where every possible outcome of every event creates a new parallel universe. It's a radical and mind-bending concept, suggesting that all possible histories and futures are real, each existing in its own universe. Lastly, we have the ultimate ensemble theory, proposed by Max Tegmark. This theory suggests that all mathematically possible structures exist as their own separate universes. Each universe corresponds to a different set of mathematical laws, making this the most expansive and diverse form of the multiverse. Max Tegmark's Level 4 multiverse encompasses every conceivable form of reality that can be described mathematically, pushing the boundaries of our understanding to their limits. These key theories and models, eternal inflation, string theory, the many worlds interpretation, and the ultimate ensemble, provide a robust framework for the multiverse hypothesis. They not only expand our understanding of the cosmos, but also invite us to consider the profound implications of living in a multiverse. The multiverse hypothesis, while fascinating, comes with profound implications and significant challenges. Let's explore the philosophical, scientific, and practical questions it raises. First, let's consider the philosophical implications. The idea of a multiverse challenges our perception of reality and our place within it. If countless universes exist, each with its own version of history, what does that mean for concepts like identity, free will, and fate? Are we just one of many copies living out every possible version of our lives? Such questions touch on the very essence of our existence, forcing us to rethink long-held beliefs about the nature of reality and our significance in the grand scheme of things. From a scientific perspective, the multiverse hypothesis presents both exciting opportunities and daunting challenges. One of the main issues is empirical evidence. How can we test or observe other universes if they are fundamentally inaccessible? This challenge of falsifiability makes it difficult for the multiverse hypothesis to meet the criteria of traditional scientific theories. Despite this, certain indirect pieces of evidence, such as patterns in the cosmic microwave background radiation or anomalies in particle physics, could potentially hint at the existence of other universes. However, interpreting this data remains highly speculative. Moreover, the multiverse hypothesis raises questions about the nature of scientific explanation itself. If anything that can happen does happen in some universe, does that undermine the predictability and explanatory power of science? This challenge forces scientists to refine their methods and rethink the goals of scientific inquiry. On a practical level, the multiverse hypothesis also influences our approach to other fields such as cosmology, quantum computing, and even artificial intelligence. Understanding the multiverse could lead to new technologies and insights, transforming our understanding of reality and opening new frontiers of discovery. In summary, the implications of the multiverse hypothesis are vast and far-reaching, touching on philosophy, science, and practical technology. It challenges us to think beyond our universe and consider the possibility of an infinite array of realities. While the multiverse hypothesis is still largely theoretical, scientists around the world are making strides in research and development to explore and understand this profound concept. Let's take a look at some of the cutting-edge work being done in this field. One area of active research is the study of cosmic inflation and the cosmic microwave background (CMB) radiation. Scientists are examining subtle patterns and anomalies in the CMB to find clues that might support the existence of other universes. Instruments like the Planck satellite have provided detailed maps of the CMB, offering valuable data for this investigation. Another exciting development is in the field of particle physics. Experiments at the Large Hadron Collider, LHC, are probing the fundamental nature of matter and energy. Some theories suggest that particle collisions at incredibly high energies could produce evidence of extra dimensions or other universes. Although we haven't found definitive proof yet, these experiments are pushing the boundaries of our understanding. Quantum computing is also playing a role in advancing our understanding of the multiverse. Quantum computers leverage the principles of superposition and entanglement, which are key aspects of quantum mechanics and the many worlds interpretation. By developing and testing these technologies, researchers are gaining new insights into the nature of reality and the potential existence of parallel universes. Astrophysical observations are another crucial avenue of research. Telescopes and observatories around the world are searching for signs of other universes, such as gravitational waves from cosmic events that might have occurred in other realms. These observations could provide indirect evidence of the multiverse and help refine our models. Beyond these specific projects, there are numerous theoretical physicists and cosmologists working on new models and simulations to better understand the multiverse. Using powerful supercomputers, they create complex simulations of cosmic events and scenarios, exploring how different physical laws might manifest in other universes. Collaborations and conferences are also vital in advancing this field. Scientists from various disciplines come together to share their findings, debate ideas, and push the frontiers of knowledge. These collaborative efforts are essential for making progress in such a challenging and speculative area of study. While we are still far from proving the existence of the multiverse, the research being conducted today is laying the groundwork for future discoveries. The journey to understand the multiverse is a testament to human curiosity and the relentless pursuit of knowledge. As our journey through the multiverse hypothesis comes to an end, let's reflect on what we've learned. We began with the ancient philosophical roots of the multiverse idea, tracing its evolution through history, from early thinkers to modern scientists. We then explored the scientific basis for the multiverse hypothesis, examining key theories like cosmic inflation, string theory, and quantum mechanics. Each theory offers a unique perspective on how multiple universes might exist and interact with our own. We looked at the various types of multiverses, each presenting unique possibilities and challenges, and considered the profound implications and scientific debates surrounding this concept. Current research in cosmic observations, particle physics, and quantum computing shows that the quest to understand the multiverse is alive and vibrant. While definitive answers remain elusive, the pursuit of the multiverse hypothesis embodies the spirit of scientific inquiry. It's a journey driven by curiosity and the desire to uncover the mysteries of our existence. Thank you for joining us on this exploration. Keep questioning, stay curious, and continue to look up at the stars, wondering about the infinite possibilities of the cosmos.